Hi, I'm Professor Melko, Chemistry PhD. Today we're going to talk about models of the atom, particularly the Bohr model and the quantum mechanical model. Last lecture we went over Dalton, Thomson, and Rutherford models and atomic notation, so we're going to pick it up from there. Go back and watch that previous video if you haven't already. This one we're going to talk about Bohr, quantum mechanics, levels, sublevels. Let's jump into the lecture. So the Bohr model of the atom was really proposed after we had experiments that were good enough to sort of detect what's called emission spectra. So Bohr, shown up here in the upper right, used this data from emission spectra to sort of theorize these energy levels in atoms. So emission spectra occur when you excite an atom. So an atom has some electrons in it. Turns out if you energize these atoms, the electrons can jump to different levels. So you might have one in energy level 2 here, that jumps up to energy level 3. And sometimes later, after spending some time in energy level 3, it can relax back down to energy level 2. When it relaxes back down, it has to get rid of some of that energy. And it does so in the form of a photon light. Okay, so that's what's summarized here. An electrical voltage can excite an electron. When an electron relaxes back down, it gives this photon off. But this emission spectra, this is what's important, is kind of like a fingerprint, right? Each element's emission spectra is unique because it has a unique number of electrons and protons, and they're organized in unique ways. So Bohr used this information to propose his model of the atom. And his was the first to establish that electrons really exist in these quantized energy levels, meaning specific energy levels, right? The electron can't live at all locations throughout the atom, only these certain orbits. And so the Bohr model is kind of appropriate to think about this nucleus that Rutherford established, surrounded by these definitive quantized orbits getting larger and larger. Okay, so kind of like a picture of our solar system with the sun at the center. Instead, here we have the nucleus at the center, surrounded by not planets, but electrons. Okay, so when electrons transition between these energy levels, energy is absorbed if they're promoted to an outer level, or emitted if they're falling back in towards the nucleus. Okay, the Bohr model failed though to predict all emission spectra. So as our experiments got better, we figured out there was light emitted where we didn't necessarily expect it based on the Bohr model. So we had to improve that by accounting for sublevels. Okay, in addition, the orbits, as they're shown here as perfect sort of circles, aren't exact perfect circles, and we'll get into that later on. Okay, so the Bohr model did sort of correctly establish this quantized energy level structure, but it sort of got the number and the shape of these energy levels wrong. The sublevels are really just divisions of these orbits, okay, and they're designated by various letters: S, P, D, F. Okay, so if we think about, again, the nucleus here at the center, right, this dense area that Rutherford found. Okay, instead of just labeling these as 1, 2, 3 like Bohr thought, there's actually sublevels. Okay, and it turns out that each level that Bohr discovered was actually divided into a certain number of sublevels. And there's a rule for the number of sublevels it's divided into. And the rule is this: for energy level 1, there's only one sublevel. For energy level 2, there's actually 2 sublevels. For energy level 3, there's 3 sublevels. So you can see the number of sublevels is equal to the number of that energy level. Pardon me. So the number of sublevels is the same as the number of that energy level. The first energy level has 1 sublevel, the second has 2, the third has 3. And we denote these different sublevels with these letters S, P, D, and F. S is always first, so in the first energy level where there's only 1 sublevel, it's an S. In the second, we have 2S and 2P. Now this second sublevel is the second letter here, P. So the third sublevel is going to be 3S, 3P, 3D. And you guessed it, this fourth energy level that is broken up into 4 sublevels is 4S, 4P, 4d, and 4f. Now, it turns out each of these different sublevels holds a different number of electrons, okay? And this is important, just something you sort of have to commit to memory, and you'll understand once we get into the notion of orbitals later in this lecture. The s sublevel always holds 2 electrons, okay? So going back here, this first energy level, which is really a sublevel 1s, you can only put 2 electrons in this sublevel. There they are. In a p sublevel, you can hold 6 electrons. Right, so in this 2s, I can only hold 2, but in this 2p, I can hold 6. D sublevels hold 10, F sublevels hold 14. So you can see the larger the sublevel, SPD to F, the number of electrons increases, and it increases by 4 each time. 2 plus 4 is 6, plus 4 is 10, plus 4 is 14. Okay, so if I'm thinking about the energy level here, 1, 2, 3, 4, the sublevels that exist, just to kind of summarize what we've talked about thus far, the first energy level, there's only one sublevel, so it's the first one, S. In energy level 2, I have S and P. In energy level 3, I have 3, S, P, and D. In energy level 4, I'll have S, P, D, F. You can imagine in energy level 5, you would have 5. We're going to stop with 4 for this lecture. Now, the number of electrons, we can count up not necessarily within each sublevel, but each overall energy level. Okay, so let's think about in the first energy level, how many electrons are there total? Account for each sublevel and add up the electrons. In the S sublevel, there's always 2 electrons in an S sublevel. There is only an S sublevel in level 1, so it's 2 electrons total. In the second sublevel, in the second energy level, I have a S sublevel and a P sublevel. The S contributes 2, the P contributes 6, a total of 8 electrons. In the third energy level, I have an S, a P, and a D. S is 2, D is 6, D is 10, a total of 18 electrons. Energy level 4, I have S plus P plus D plus F, 14, for a total of 32 electrons. So if you're asked how many electrons fit in the third energy level, that's 18. If you're asked how many electrons fit in the 3p sublevel, that's 6, because there I'm making the point that it's just one of those sublevels, not the entire energy level, which has 3 sublevels. Okay, so be careful with the semantics there. The periodic table has all this information hidden in it. This is why, chemists love the periodic table. It stores so much information. Okay, and it stores this when we think about this first sort of left shoulder here of the periodic table. We call that the S block. It is 2 elements thick, and S electrons, we've just learned, hold 2 electrons. S sublevels hold 2 electrons. This sort of shoulder on the right here is known as the P block. We just learned that P sublevels hold 6 electrons, and that is why this P block shoulder is 6 elements wide. Okay, remember, each element is sort of increasing here by its atomic number, which is the number of protons, but when these things are neutral, they also have that many electrons. So as I add each proton, going from boron to carbon to nitrogen, I'm also adding an electron, and I'm adding 6 here when I go from boron all the way to neon, and that P sublevel holds those 6 corresponding electrons. This central area of the periodic table is known as the D block, and you can probably guess now how many elements wide that is. A D sublevel holds 10 electrons. That's why there's 10 elements in this D block. And down here, these are the F block elements. And it's no surprise going back here that that F block is 14 elements wide. Okay, so the periodic table is sort of a shortcut to remember some of these numbers because it has them visually within it. Now, sublevels increase in energy as they get further from the nucleus. Okay, so remember, I drew these sublevels in a particular way in this terrible drawing down here at the bottom, right? Getting further and further away, you're adding up energy levels 1, 2, 3, 4, but you also have 1s, 2s, 3s, 4s, etc. Turns out I didn't draw them exactly correct. That was just for my example there, but they're organized slightly differently. And this is how they're organized. So if I have the nucleus here, the first sublevel I get to is 1s. The next sublevel I get to is 2s. Then I get to 2p. And so far, this makes sense, right? The energy level is getting greater. 1, 2, 3. 4 will be even further out. And the first energy level has one sublevel, 1s. Second energy level has two sublevels, 2s and 2p. Third energy level has three sublevels, 3s, 3p. (3d). But notice here, 4s actually comes in between. Okay, so this is the tricky part, that in this fourth energy level, you know, this width of the third energy level is such that the outermost third energy level, 3d, actually comes after the innermost fourth level, 4s. So 4s would be here actually closer to the nucleus than 3d. And so as I'm adding electrons, the electrons want to be close to this nucleus. Okay, so the first two I add in here, and they fill up the s sublevel. The next two go here and fill up that s sublevel. The next 6 can fit in here. Electrons, negative, they want to be close to this positive nucleus, but there's only so many spots they can take up. Right? The next 2 will go in this s. The next 6 will go this orbit, right? So these dashed lines here are the orbits, right? I'm not just drawing the full circle because I don't have the room. After that, I can't go to 3d. I go to 4s first for the next 2 electrons. And then after that, I jump back to 3d, and I can put 10 electrons in any d sublevel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so electrons fill this lowest or closest to the nucleus energy level first, right, before going further and further out. And the sublevel is filled up with electrons until it reaches its maximum, 2 for each s, 6 for each p, 10 for each d, 14 is the max for f. Okay, so you can have a shortcut to remembering how to fill these up in these rules, right, and these exceptions, like 4s comes before 3d, by using a chart like this. You can write out the energy levels down the left, 1, 2, 3, 4, 5, 6, 7, and then S, P, D, F, going from left to right. Okay, the first column, I write 1s. The second, I write 2 of them, 2s and 2p. The third, 3, 3s, 3p, 3d. The fourth, 4, 4s, 4p, 4d, 4f. And then the sublevels are filled in this order, drawing arrows down and to the left. And when you get to the end of one arrow, you sort of come back here to the next arrow. All right, so following this through, I go through 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and that's probably for most things as far as you'll need to go out, right? Again, that's summarized here in this ordering. But this is sort of a mnemonic, or not a mnemonic, I guess, but a visual you can use to keep this ordering of sublevels in mind. Now, the reason we're going to worry about this ordering of sublevels is to write and understand electron configurations. It turns out that a lot of chemistry is just dictated by what the electrons are doing. And so scientists and chemists, we really want to keep track of where are the electrons. I want to know for a given element how its electrons are organized, because then I can sort of predict what kind of chemistry that element undergoes. And so the electron configuration denotes the location of an electron in a particular atom. Okay, and the way we write this notation, scientists always have shorthands. It's no exceptions here. The electron configuration is just a shorthand. We're going to write the number of energy level, followed by the lowercase letter for the sublevel, and then a superscript for the number of electrons in that sublevel. Okay, so if I know there's an atom with only one electron, it's going to go in the first energy level, and it's going to go in the S sublevel of that first energy level. That is the only sublevel in that energy level. This one electron will be found there. Now, if there's two electrons in an atom, and only two, okay, they're going to go in the 1s sublevel. A max of 2 can fit. If there was 3 electrons, I can't fit a third in this first S sublevel, so I have to go to the next available spot. The next available is the 2s, and this third electron would live there. If there's 4 electrons, well, I can fit all 4 like this. If there's 5, now I have to put one in the next spot, and so on and so forth. Okay, so this is the electron notation here for the electron configuration: energy level, sublevel, number of electrons. Okay, so let's see this with an example. We can write out the complete electron configuration for any element. Here we're going to do bromine. And if we go to the periodic table, just have one here. Here's bromine, 35 electrons. Okay, so we're going to write, and we're going to fill up in this order all the electrons. I know there's 35. I'm going to recall the ordering of the sublevels. I can either use this shortcut or just commit to memory the ordering: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, etc. I'm going to write all those out, and now I'm going to start filling in these 35 electrons. Starting with the lowest s, 2 electrons fit. Moving on to 2s, 2 electrons fit. Moving on, next is 2p, 6 electrons fit in the p orbital, or p sublevel. Next is 3s, 2 electrons fit there. Then 3p, 6, 4s, 2, 3d, 10. And I have a maximum of 35 electrons. So far I've used 2, 4, 10, 12, 18, 20, 30. So I have 5 more electrons to go. 4p, I put 5 electrons there. I don't have to use these higher energy levels because I'm out of electrons. Okay, so we stopped at 4p5 since all 35 electrons were used. We don't include the later ones. The sum of the superscripts, as I sort of did there, will add up to this total number of electrons. Okay, so be able to write this electron configuration for any element. Right? Again, start with the atomic number. That'll tell you the number of electrons. Write out your sublevels, and then start putting the electrons in until you've used up all those electrons. So let's take a moment and practice that. See if you can pause the video here and write the electron configuration for a neutral beryllium atom. Beryllium is found here on the periodic table. Its atomic number is 4. 4 protons, 4 electrons, since it's neutral. So I know there's going to be 4 electrons used here. If I think about the energy levels, 1s, 2s, 2p, 3s, 3p, I could keep going, but this is a small atom. There's only 4. I'm probably going to run out here, right? Starting with the closest to the nucleus, 1s, 2 electrons can fit in there. Okay, so now I've used 2 of the 4 electrons. There's 2 left. I can put the next 2 in the 2s. And now I've used up all my electrons. So I don't need 2p, 3s, 3p, 4s, or anything else. This is the whole electron configuration for beryllium. The last model of the atom is the quantum mechanical model. And this is what we still use today. This is the most accurate model of the atom that we have. Doesn't mean that tomorrow something bigger and better might not come forward, but all the experiments, all the evidence, the technology we have today suggests this is the correct model of the atom as we know it. And quantum mechanical model of the atom sort of extends the Bohr model using one really large change. Okay, and that's all thanks to this creepy looking gentleman here, Heisenberg. And the Heisenberg uncertainty principle suggests that we can never know the exact location of an electron. Right? So it's not exactly correct to draw these little electrons in this orbit as being exactly here. Okay, it turns out we can't actually know that. We can never know the precise location. All we can really know is the probability it's found in a certain region of the atom. We don't know exactly where it is, but we might know it's a high likelihood of being a certain distance away or in a certain area of the molecule or atom. Okay, so the electrons don't have these definitive orbits. It's not correct to think of them as planets around a sun. Right? The Earth, we know, has this certain sort of distance and location in the solar system, respective of the sun it's orbiting. It's not correct to think of electrons and atoms in the same way. Okay? We can only think of areas of high probability, and we don't note these by orbitals. So it's not orbits, they're not definitive, but they're orbitals, probabilities, and approximations. Orbitals are arranged according to their size and shape, and it turns out that the sublevels are really different orbitals. So we have an s orbital, like we had an s sublevel, we have a p orbital, we have a d orbital, we have an f orbital. Importantly, we also have energy levels, 1, 2, 3. Okay, and the number describes the size of that orbital, right? Just like we saw the larger numbers denote larger orbits, larger numbers are really denoting larger orbitals. Okay, and larger orbitals have larger energies. So again, it's really just a probability. The 1s orbital, that's this sphere here, denotes a region of space where we really are confident the electron is. We don't know what point within that space the electron is, but we're pretty sure it's within that sphere. Okay, 2s is larger. We're pretty sure the 2s electron is somewhere in this sphere. The 3s, higher energy, is a larger sphere. We're pretty sure there's a high probability the electron is somewhere in there. So it turns out for these s orbitals, we can think of the s standing for sphere. It doesn't really, but that's how we can think about these to remember the shapes of these orbitals. Okay, so again, the number denotes the energy of the orbital, and also increasing numbers mean increasing size. All s orbitals have these spherical shapes, and each sublevel has one orbital. Right, so that is to say that 1s, there's an orbital for 1s. For a 2s sublevel, there's an orbital for that. So the sublevel is sort of the same as an orbital. And we said 2 electrons occupy every s sublevel. Really, they're occupying the orbital. So each s orbital holds up to 2 electrons. It might hold just 1 electron. If we run out of electrons and there's not another one to pair with it, it could hold no electrons, right? Maybe we don't get enough, maybe we don't have enough electrons to fill all the way up to 3s, so there's no electrons. But the maximum is always 2 for an s orbital. P orbitals have it says dumbbell here, but I like to think of it as a peanut shape. S for sphere, P for peanut. And each p sublevel has 3 orbitals. So unlike the s sublevel, 1 orbital, a p sublevel has 3 different orbitals. Okay, 2 electrons fit in each orbital. So here's 2, here's 2, here's 2, and this is why the p sublevel in total holds 6 electrons. Right? Similarly, the s sublevel held 2 because there's 1 orbital which is holding 2. Here the p sublevel holds 6 because there's 3 orbitals and each orbital holds 2 electrons. Okay, so each p sublevel has 3 orbitals. The 2p sublevel has 3 orbitals for 6 electrons. The 3p sublevel has 6 electrons and 3 orbitals. The 4p, 6 electrons, 3 orbitals. Every p sublevel has 3 orbitals and 6 electrons. Maximum of 6 electrons. D orbitals, I don't really have a clever nickname for this. I think they look like clover leaves, especially these 4. There's a last one here that kind of looks like a peanut and a dumbbell. But these are 5 different d orbitals. Okay. Remember I said that the d sublevel holds 10 electrons. And if we know every orbital holds 2, then there must be 5 orbitals. And that's exactly what we see. Okay. Every d sublevel has 5 orbitals, 2 electrons in each, for a total of 10 electrons. Right. So going back here when we were first learning about these numbers, S sublevel holds 2 electrons. That's because it's 1 orbital, always in an S sublevel. The P sublevel holds 6. That's because it's 3 orbitals. The D sublevel holding 10. That's because it's 5 orbitals. And there's 2 electrons per orbital. So 1 times 2 electrons is 2 electrons. 3 times 2 electrons is 6 electrons. 5 times 2 electrons is 10 electrons. So how many orbitals are in a F sublevel? There's 14 electrons total, so it must be 7 orbitals. Okay, so this is now extending this idea of sublevels, which was sort of incorporated from the Bohr model of the atom, to orbitals, which is very much a quantum mechanical model of the atom that sort of Heisenberg ushered in. Now, again, we can sort of consult the periodic table to understand this, right? This S subblock, these are all sort of S orbital elements. Here's the P subblock, 6 elements. That's because there's 3 different P orbitals, each holding 2 electrons. D subblock is 10. The D block is 10 elements wide for those 10 electrons. The F block is 14 elements wide for those 14 electrons, or 7 orbitals. Okay, I think that's where we'll stop things here. We sort of talked about the Bohr model of the atom, the quantum mechanical model of the atom. This terminology gets very confusing very quickly, so take some time to read about this, watch this video a couple of times, make sure you're understanding the differences between energy level, sublevel, orbital, electron configurations, okay? Because it's easy to get tripped up on a written question unless you really have spent the time visualizing and thinking about these different concepts. That'll do it for today's video. I'll add some practice problem videos for these concepts coming up. As always, you can subscribe to my channel for more videos like this, or catch me over on Twitch, where I do office hours every week, and we also do science news discussions. So that'll do it for energy levels, sublevels, and orbitals, and quantum mechanics. See you next time.